you for joining us today. Thank you for joining us, and on this St. Patrick's Day. This is the March 2015 edition of the Community for F# live meetings, or as they're now being run through Hangouts. I guess this is a Hangout. Today we are pleased to have Riccardo Terrell. He works for Microsoft and is going to be talking to us today about the actor model in F# using Akka.net. So Riccardo, thank you so much for joining us, and we look forward to what you have to say.
Hello everyone, and thank you for having me, and thank you for joining. So Ryan, just double check with you last time. You can see my presentation online. It's all good to go?
Looks great.
All right, very well. So yes, as Ryan mentioned, my name is Riccardo, and I'm today going to present about actor model in F# and Akka.net. Briefly, this is the agenda about the presentation today. We're going to have an overview about what's going on out there, the new request on demand of the technology world. Briefly about the Reactive Manifesto. Of course, we discuss finally about the actor model, what it is, and why you should interest about the actor model. I want to mention a little bit about the F# agent, I mean the Mailbox processor, because there is some confusion about what is an actor, what is an agent. And I want to just spend probably just 2 slides about the difference. And then moving forward to the Akka.net in action, and of course the beautiful F# API. All the slides and the code sample that I will present are already in GitHub. And in the end of the presentation, you will have the link where you can download all the material and play with. So, just briefly about me, I'm originally from Italy. That's where my accent comes from. I'm living in Washington, D.C. area, and I have more or less 16 years experience in professional programming. I'm the organizer of the DC F# user group. As Ryan mentioned, I currently work for Microsoft, and I'm passionate about technology. I like to play with languages, always looking for the right tool for the right job. And the goal for today, so I will cover a lot of information, and honestly with you, when I first start the presentation, it was 2 hour just slides, just about slides, and an hour code sample. So I narrowed down, and we spent probably 30 minutes in slide for high-level concept, and then moving forward with Visual Studio and do some coding and check the actor model in action. But I will provide 3 objectives that I want you to take away, and this is that the free lunch is over, right? We are facing the new challenge today in technologies, and we have to face this new challenge. And today, application must build with concurrency in mind, and I put between parentheses posting from the beginning because it's hard to convert an application from sequential to concurrency unless, of course, you are not a functional programmer, but hopefully you are. And of course, the actor, I'm a bias, I think is the best, but is a great concurrent programming model to solve problems such as scaling up and scaling out, which probably the main reason why you would like check what an actor provide in the solution that can provide to you. So we've seen that the last 10 years, there have been significant changes in the world of computing, right? In today's world, the domain of the distributed system has exploded. And the customer, the user finally has high expectations, such as, they want the data now, they want immediate responses, and there were no failure, right? They don't like, the yellow screen of that in an SP application. And they want request to, they want access to internet everywhere, and this demand is increasing more and more. And of course, with this demand, there's also the requirement that come to build our application or change. And if you search right now online, for what is really trendy right now, you can see all these great technologies such as mobile application, cloud computing, single-page application, and all also require to interact with big data, right? So it's very complicated. How do we achieve this, right? how we combine this architecture, this language, to make it possible to write programs that overall are scalable, maintainable, readable, composable. I mean, we want our application that respond all these characteristics, right? So it's not easy. So this is our couple of quotes from some published book, and you can read the slides, but what really mean is that there is a new landscape out there, right? There is this distributed cloud computing that really represent a dramatic change in today's computing. We have we can compare today versus yesterday, and the main difference is that today we actually are doing something with bunch of data, right? We have this thing called big data, and we are not just as we used to keep track of the data or moving data between server or store the data, but so in the end somebody can get this data and analyze this data, maybe with Excel, some spreadsheet or software. Today this is not possible anymore. We have this enormous quantity of data that we have to deal with, and what make important to us is create software that make machine analyze, compute this enormous quantity of data ahead of time and possibly in a short time. So it is hard, this is the problem, because overall it is hard to build, correct high concurrent system, and there's also truly scalable and possibly fault-tolerant. So these are the key, and also these are the problem that you're facing today. So, and with this problem, I mean, with all this question and this problem, that we see the rise of answers, right? So one is the Reactive Manifesto that actually has been recently updated, I think September, October. And what this really means is that the world is going reactive, and there are a number of ways that you achieve this goal. So the concept that you see in the slide that the Reactive Manifesto makes are case for what really your application need to be to achieve this model. So briefly, the application need to be responsive, and this means that the system must work no matter under what kind of stress, right? Can be heavy load or low load or a very low load. It doesn't matter. It to be responsive in the same time. And not only because the user really doesn't care what's going on under the hood of your application. You just want the application running. Message-driven architecture is mean that this kind of architecture is very loose coupled, is asynchronous and no blocking, and these are the key of the application to be scalable, right? Asynchronous application is able to execute tasks without blocking, and this is provide a very responsive application. Resilient means that the system react no matter what, if it's fail or there is some crash, right? Resilient means that the application can self-heal, that the application can bring back in shape the system without any problem. And there are several ways that you can achieve this goal, the resiliency. And the secret that we'll see actually later when discussed about the supervision in actor model, but it's really about managing isolation and the recovery in an isolated manner. So elastic, this is also the key for a distributed system, and this means that the system can grow or can expand or contract on demand depending upon the change on demand. So, well, I think that in the last year you've seen this slide several times. Actually, I really like this slide because really you can see in blue the trend of the speed of the course, and in red the number of the course per years. So, and what it really doesn't mean, this slide, is that there is really the need for a concurrency programming model today, because there is the evolution of hardware toward the multi-core, right? They bring us new challenges as a programmer, and as a professional programmer, we are looking to answer this challenge in a proactive manner, because this problem is real, it's present, and everybody today has devices with at least more than one core. So this slide really represents the fact that programs and our software cannot anymore leverage one single very fast CPU that we know increase every year as Moore's law predict in 65, right? Instead, programs need to be run in parallel and need to take benefit and leverage all the CPU that your machine has. So the free lunch is over, and these days, more and more in the future, computer and machine are shipped with multiple cores. Is a reality, and this is great because it's able to process number of tasks in the same time. But with that, we have to face that we're programming. The majority of us still program with languages that weren't designed with concurrency in mind. So we write code that is sequential and that is executed just like in a single stream of operation. So we are here, in a Sharp community, and I'm assuming that everybody is familiar with the functional programming style, and we know that out the box, this paradigm really support as an excellent support for concurrency and parallelism, because it eliminates problems such as mutable state and isolation. Sorry, mutable state. So it's common. I think everybody knows that how hard it is to write concurrent applications. It's extremely hard, but probably I should say that it's extremely hard to write correct concurrent application. There might be race condition, unnecessary block your application, and to solve this problem, we used to use primitives such as log, semaphore, mutex, and you start using this primitive, but the problem is that there is not really a tool, debugger, or compiler that can warn you and tell you that you put the log in the right place, right? And you think that your application ran correctly, you send in production, and 6 months after there is some problem, some race condition, and I dare you to try to reproduce the bug, right? Use the log in some sort of computation, and probably is necessary only for once every 10,000 calls, and at the same time you downgrade the performance or your computation because the logs equals every single time, no matter what, even if you need it probably only once every 10,000 times. So, as you can see in the slide, this is the classic, way that we used to write programming in an imperative programming style, which is very sequential and promote the immutable state. As you can see here, if two threads run in the same time in the same method, well, you don't know if thread 2, in this case the thread red, you don't know in which state left our account, our balance in our bank account, and that can create some strange behavior in our application. So to solve all these concurrent problems, the solution is really remove the problem at the source, right? And write function that bring on the table this concept such as immutability and isolation. So immutability, besides the fact that it is allowed to write correct concurrent application, it also gives us a power to reason about the behavior of a program, because as I mentioned in the previous slide, you don't need to know in which state, you have to check in which state the thread left our object because the object didn't change, right? So immutability can prove that our program is correct, run correct. And when a program is designed with this kind of approaches like transformation, it really becomes easy to be scalable with some simple tweaks. So using isolation and mutability, it doesn't make your application run faster, but it makes it ready to run in parallel easily. So this is the Mailbox processor in F# implementation. I just type alias the Mailbox with agent, like I think everybody does. But the idea is that because the agent, and we're going to discuss deeper later, is a thread safe and run in a single thread, all the types and objects inside the agent are isolated and thread safe. So it's okay to use mutable object. In this case, I use a mutable dictionary inside my agent, right? Because it's isolated. So it's a very powerful concept. So immutability and isolation still are really the ingredient for the recipe for our secret sauce. And F# borrow the message passing process mechanism from Erlang, right? There is this notion about share nothing, and it might seem a bit extreme in the beginning, but there are very powerful concepts that come from the fact that you don't share, you don't share your types, your object. So we discussed that the actor is an independent computational entity, right? And provide out-of-the-box immutability and isolation. And this is enforced to the fact that the actor can communicate only through message passing. And the message are passed by values, so it's just so they're immutable. I think about an actor as an internal queue that contains all the messages received and parse and process one message at a time. So what is an actor, right? Well, this is a definition that you can find in Wikipedia, and boil down to the fact that an actor model is a very general purpose concurrent programming model. It does provide support for concurrency, but not just that. You know, it provides other benefits as a state machine and so on. I will see later in an example. But I found this very nice example in one book. I forgot which one, but they really was comparing the actor as a rental car. And you can get a rental car quick and easy. Just, you know, you call your rental company and you get one car. And if it breaks down, you don't really bother to fix your car. You call your rental company and get another one, and they deliver it to you. And this is pretty much very similar to the concept of the actor, right? You run the actor, you send message to the actor, and we see later with Akka.NET with supervision, if the actor breaks or crash, you don't care. It just the supervision just create a new one and deliver to you a new actor. So again, as I mentioned, an actor is an entity that hides this isolated message queue inside the mailbox body. And what is nice is that the actor is reactive, right? It reacts when it receives messages. So, for example, an actor could have usually an internal loop asynchronous in the body, and it waits for message to come to be processed one by one. So there's also, we discuss later, it's very lightweight in actor because, as I mentioned, it's reactive. When an actor is idle, it doesn't have any message, there's really nothing to do. So the thread that owns the actor is back to the thread pool and without consuming extra resources. And only when the actor receives a message, then the actor go back and process the message and move forward. So you can really have a bunch of actors in your system and without a heavy payload on your resources. And I like to think the actor as this is the DC metro map. Think about the actor as metro station, right? They're all independent metro station, and they receive train coming in or coming out. There are messages, and a train is passenger, so they process the message and so on. But what really is important to take from these slides is the fact that actors are independent unit, right? It's like the train station. What they care is just receiving the income training, even train, like the messages. They don't care about train station located in another area. So, what's really interesting is that the actor model is originated 40 years ago in 1973 by a paper that wrote Carl Hewitt. And actor really raised the abstraction level and provide a better way to build correct concurrent and scalable application log-free. So in the paper, Carl Hewitt said that there are 3 axioms in the actor, and the actor can create more actor, send messages to other actor, and determine how to respond to the next message received, meaning it can change their own behavior, right? You receive a message and analyze the message, process the message, or is a message to tell the actor to become something else and react in a different way for the next income messages. And the point here is that Carl Hewitt pointed that one actor really, because communicate with another actor, a system of one actor is no actor. Actor always come in a system, in numbers of different actors. The first major adoption in the 80s was from Erlang, which was a very successful story. And then there are other successful happy-handed story, like everybody know WhatsApp, and Twitter used the actor model in the back for the message processing, Facebook as well. So you can see big company with a high distributed and fault-tolerant system use the actor model in the back. So as I mentioned, Erlang is a great story, successful story, and it is so successful that everybody know the myth of the 9-9ers, right? In the 96, they create this switch for the telephony industry, Ericson, and it was able to be down 30 milliseconds per year. And what really crazy to me is how we're able to measure that, right? Is so powerful, 9-9ers per year, that it's like perfect. So, as I mentioned, there is a difference between an actor and an agent. F#, and I personally use F# Mailbox processor heavily in one of my current application that will be in production actually the end of this month, very successful. And it's great that F# is baked in the language, this technology, and beside the Mailbox, also known as the agent, in the async workflow, really F# shine in the area of distributed computing. But there are some problems with the Mailbox processor, right? Well, this is just briefly how I think everybody is familiar, but just to have a high level how the Mailbox processor is created. You have the Mailbox that has an income, asynchronous loop that wait for message to arrive and process them, and probably also asynchronously reply the message to the sender. What you can notice here in this slide, well, you create a Mailbox processor and you instantiate an agent. So you can reference an agent only in process. This is really a explicit reference to the agent. So there are a few problems with the F# Mailbox processor. One, first of all, is no cross boundaries. The process, the F# agent really live and work only in the same process. You can overcome this issue writing your framework, but it's not trivial. Agent, as I mentioned in a previous slide, only referenced by an explicit instance, right? You can now reference by address. And this is also makes sense as the implementation of the agent had in mind to run only in the process. The queue inside the mailbox is not durable, meaning that the agent crashed. Besides that, probably can crash and bring down also the process with him, but really lose the state that was inside the agent. So, and of course, this boils down to the fact that agents don't have any sort of routing, supervision functionality in the box. So this is the difference between an agent and an actor, right? An actor, we see actually an example, is cross-boundary, has functionality to be fault-tolerant with supervision, and because it's cross-boundary and built-in, back-in functionality for routing to dispatch messages to all other actors, different nodes that are listening and waiting for income messages. And one actually important difference that I almost forgot to mention is that the agent, think about the agent because it's in process, is function like a memory slot, right? So the difference between agent and actor, well, not completely going to see actually how you can do the same functionality with an actor, but with agent you can, beside messages, beside data, you can send function, meaning that you can send behavior to the agent, right? And this is actually provide a very nice way to write function and compose function before send this compose function to the agent. So finally, Akka. Akka.NET is the port of the popular Java framework Akka to the .NET platform, and really define itself as a toolkit, a runtime for building high concurrent, distributed, and resilient application. So, and we see later, I really want to convey to you the fact that Akka is a tool set that you really should have in your tool belt to write high distributed and fault-tolerant systems. So, Akka is used to achieve better performance in providing a very simple programming model, especially with the F# API we'll see in a moment. So there are several great characteristics about Akka. Of course, we all know at this point Akka is all actor-based, and all the computation run asynchronously, no blocking inside the mailbox, inside the box of the actor. Is fault-tolerant, is really baked in supervision and embrace the let it crash philosophy. And of course, is great for distributed computation and approach the idea of location transparency. And we're going to see an example. The user really can send messages to an actor, and really it doesn't know and probably don't even care if the actor is local or is remote. Lightweight actor, because again it used the thread pool in the back, is a very small memory footprint, and the difference is that like one thread is about 1 megabyte of memory versus an actor is about 400 bytes, and the difference really you can have a little bit over almost 5,000 thread per gigabyte versus 2.7 million actor per gigabyte. And I know that the number seems crazy, but this means that you can create a bunch of different actors and in your system and be more free how express your program. So, what kind of problem Akka can solve, right? Well, at this point we know is distributed is great for distributed system. Akka provide a high-level abstraction for concurrency and parallelism, and Akka give us the ability again, thanks to location transparency, to communicate across node in a very transparent manner. As I mentioned, is asynchronous, is a no blocking, and that's the answer for event-driven application. And of course, all put together, Akka provide a simple programming model to write high-performance application. It's really able to handle tremendous load and fast react to the message sent, and also at the same time be fault tolerant, right? So ultimately, as I mentioned in the beginning, we talked about the Reactive Manifesto. Akka really is able to answer all the questions for building React application. And Akka is event-driven per nature, as communication are all passed by messages, and of course resilient for the supervision and elastic because all the remoting functionality built in a framework or toolkit that they like to call. So we talk about resiliency and fault tolerance, right? So how do you keep your actor from falling apart when something goes wrong? Well, we talk about supervision, and supervision really is the concept that allows your actor to quickly isolate and recover from failure. And supervision really ensures that if something goes wrong, this failure will be contained in the actor, and the supervision really gonna self-heal the system and resume, restart. There are different kinds of strategies you can apply to heal your system. In fact, how the parents can solve the error, right? Well, there are two factors that you can use, two ways you can use to resolve the failure. One is check how the child failed. You have completely control to check what kind of exception the child raised and apply different strategy. And really, what is important and take away, especially from the Erlang experience, is to embrace the let it crash problem, right? Because let's face it, at one point your system can crash, and you used to have to adapt and the very defending programming model, put your try catch everywhere and be paranoid, probably losing hours of sleep over, and your system crash anyways because there are portion of your application that you're not in control. Maybe the network, or can be a disk failure on your system, and so on. So just the idea that Erlang promotes is the let it crash philosophy, which just think about that the crash is just a different state of your application, right? Your application can start, run, and can crash. So don't worry about it, just let it crash and deal when it's crashed, when it's happened. So just briefly, there are supervision I mentioned embrace the let it crash philosophy, and the idea the supervisor use the arrow kernel system, which is a part of your application that must be always correct. So this is why the best practice is really to build your arrow kernel smaller and smaller, so it's less prone to error. And this is the secret that Erlang used to build, system 99ers uptime per year. So there are different kind of strategies, but the two more important are one-for-one supervisor. And the idea is that if one node crash, it really doesn't matter. The system is gonna restart the node in the specific route and restart it. Or all for one. And what does it mean is that if one node crash, all the siblings that belong to the node will be restarted together. And this is important. Maybe sometimes you have some share between the actor that you want to be sure that the state is consistent. Well, briefly, because I probably want to run some code here. This is just how you build your strategy. So this is use the F# API. So you spawn an actor and you pass the option how you want to implement the strategy. And we'll see actually more sophisticated example in the coming code sample. So remoting, as I mentioned, is designed, Akka is designed to work in a distributed system. And as this remoting built in the framework, which allowed to send messages to other actor in a transparent manner. And this is the secret how Akka.NET reached the goal of high performance, actually primarily very scalable application. So think about as a bunch of nodes in your system, and they actually can be break apart in different systems. But what is important here is that the user, when send a message to an actor, it doesn't know that the system actually is, and the message is sent to system 1 or system 2. This is all taken care for you underneath. And that's thanks to the location transparency that I mentioned a few times, which is the secret to create applications that are able to scaling up when you have multiple actors in the same machine, or scaling out when you can send the same message to node located in the network. And what is very awesome about this is that the code doesn't change, right? The user just send a message. That's it. So location transparency here, meaning is really the fact that the user don't need to know in which system the actor, system the actor belong when you send the message. And here in the slide, you have the path where you have your system. You pass the address of your machine, and the path that actually is the node. It can actually move forward to the child, and the child, and so on. And we have an example about that. So, well, let's move on here. Okay, here, if you really want to, talk about Akka.NET and F# to your friends and tell something super cool, well, this is probably what you want to talk about, the hot swapping. And F# shine in Akka.NET because you can leverage the code quotation, and you can serialize an actor and spawn an actor remotely, and the system that is waiting on the other side, you get this message with the serialized actor, deserialize it, and spawn an actor remotely. So really you can full deploy an actor in a different system using the F# API code quotation, which is pretty awesome. I have an example about this coming. So routing, well, as I mentioned, the routing handle the fact that you can spawn multiple instances of an actor in the local machine or different node and actor without know actually what's going on underneath. And there are different kinds of strategy that can you apply to the routing. Let's move forward. One is the broadcast strategy, where the messages are sent all to different instances of the actor to the router. And this is useful when maybe you want to send a message to different actor, and each actor has a different implementation how to process the message. So you send out the message, and each actor sees the message and processes in a different way. And then, of course, we have the round-robin strategies, which is probably the most used, which is great for scaling up and scaling down. And what it does is just the actor send the message in a round-robin fashion, the message to each actor part of the node. And of course, you have the grouping when you have several actors part of the same group. This is how you can break down the scaling out, scaling up. Probably you have a round-robin pool that send a message to different machines in the network, and each single machine have a round-robin group built in the node. But we have an example about this to be more clear. Again, actor is great for distributed system, but not just that. Actually, the application that I building right now, I use the actor not for concurrency at all, but just to create a very solid multiple state inside the agent. And you can see in the slide, you can change the behavior of the actor, just send a message and tell it to become something different, right? I think everybody familiar with this kind of approach, if you're familiar with the Mailbox processor in F#. So, well, let's get started. I think time to move in Visual Studio, but just to say something about how to start with Akka, you just install the package, come with Nugget, and the F# API. And I think it's time to go in Visual Studio. Let's go to the demo slide. I think I'm going to show this code in a demo. So let's see how to. So, all right. So let's see. All right. So I think we're gonna. I'm able to take questions at the end of the presentation. Probably will run a few minutes after the 1 hour, but I want to show you something very important about how Akka really looks. So there are two ways that you can create an actor in Akka.NET. One is an imperative manner, and one is leveraging the awesome F# API. And so this is an example how you can create an actor in an imperative manner. So in this case, I have an actor server that inherits from our actor type, and this is an untyped actor. So there are two types of actors in Akka: the untyped and, of course, the type. And you can imagine the difference that the untyped actor just received a message that, as you can see here, the message is a type object. And so what you can do is just use pattern matching and using the test operator to figure out what type it is the message and process the message according with that. So let's run this code in my REPL here, and hope you're going to see the result. Or probably let's move it here. Okay, probably that's better. So I create my actor. Now I create my system, as you can see here, and I create my system called F#. So now the system is really the root, is the reference that all the underlying framework of Akka.NET works. So when you create an actor, you always use the system, sort of like your actor factory. So you create your actor here, and you pass, message. In this case, I pass a string. As you can see, the result is hello F# because it was waiting for a string to react as print in the console the hello. If I pass an integer, because I'm not handle that, it just print the different message in the console. Another way that you can create an actor, still a little bit imperative manner, you specialize your receive method inside the actor. So you create an actor using the receive actor type, and then you specialize each method with the type of method that you want to handle. And each method you can use in your pattern matching to deconstruct your message and process your message according with the purpose. And here, line 38, there is also this method that you can override, which is called unhandled. And this is pretty much compare one-to-one to the previous code with the untyped actor that just received messages. So when you send a message to this actor, if it's not the message type that you intend to handle in the to specialized receive method here, is going to handle to the unhandle method. And the user, this is used mostly when you create maybe some dead letter logic for the actor. So again, I send my actor to my RAPL here. I create my system, my actor, and now I can send the message to the actor, and you can see print type 0 as the first print. I increment 3 times and I print 3. Or I can use the other message type, which is literally called other message, to decrement and display the result. And if I pass a string, which doesn't belong to any kind of message type that I want to handle, so my handle message get this message and process it. So interesting to note here in the RAPL, I highlight when you create an actor, is also return an actor ref, which is not an actor reference that like in F# when you create an agent or a mailbox processor. It's just create an actor ref that can be used to reference an actor by address. In this case, this is the address of the actor, or per se the actor reference. So this is how you implement an actor in an imperative manner. So we are here because we love F#. So let's see how this F# API works, right? Well, as you can see, quite different. There is this spawn function that you take the system, the name of the actor, and a function that represents the body of my actor. And inside the body, there is this actor computation expression that really handle a sort of recursive asynchronous loop, and you can access the mailbox in this computation expression to receive message or send back the result to the senders. So let's run what is called in RAPL here. I can select the actor. In this case, just for the sake of the example, as I just previously mentioned, I can select the actor using the select function, passing the address of the function and the system that the actor belongs. As you can see here in the RAPL that I like, this is the address of my current actor, and I can select this actor just using my select function. At this point, I can just send messages and print the result here in a string. So this is pretty cool. We're going to talk about configuration in a coming example. So far I demonstrate, I show how you can create an actor in an imperative way or using the F# API way. But what about if you wanted some answer back, right? So everybody probably will send some sort of computation to the some sort of computation to the actor and receive back the result of the computation. So in this case, I create an actor using F# API. I send a message. In this case, it will be URI that contain URL to download a text file. The mailbox run my function from URL that downloaded the string of the file, and then you can see here in line 50, I send back to the sender the response. So mention F# API have two infix operator. The left arrow bang when you want to send back a response to the sender, or left arrow question mark when you send a message to an actor and you're waiting for a response back. So let's run this simple code here. So I create my actor, and now my actor, I can send 4 requests here with timeout to the actor. The actor, the echo server actor receive the request, process my request, downloading the file, and send me back to the sender my response, my result, and I print out the result on my RAPL here. You can see the result. So this is great, but there is a problem, right? Well, the problem is that we like to write asynchronous processing, right? You can see the from URL is asynchronous. It's just run sequential. So we like to write code asynchronous, and so we're familiar with F#. So how about run our process in our async block of code? Well, it's not recommended. So this is Akka.NET and the Actor work a little bit different than the Mailbox processor in F#. And the problem is that if you run the code that is here on the screen, what it does really, the actor receives the message, compute the message with our asynchronous computation, and because it's asynchronous and I run as in a different thread, the actor is moving on and grab the second message in a queue waiting, and this can break something. Think about if you have some sort of state in your actor that you want to keep consistent, and really you want to keep the computation inside, isolated in a mailbox, and left the actor moving forward only when the asynchronous computation is completed, right? So as I mentioned here, don't run this code, right? It can be very dangerous. You can run some behavior. But the answer, there is the pipe2 function built in Akka. And the goal behind pipe function, as I write here in the comment, is really to treat every asynchronous operation just like a method, right? It just compute the message and wait for the result in asynchronously, so without blocking the current thread. We have the fix operator to replace the pipe function because we like fix operator in F#. And what it does is just we still use our asynchronous block computation expression and run it asynchronously, but still waiting for the result. So the change in the code that I did, I changed my function to download the file to run asynchronously, and then I run asynchronously inside my actor, right? So let's run this code, and we're expecting the same behavior as before. It's just that we know that the computation is run asynchronously and provide us a way to develop application, more scalable application. I can create, in this case, Echo Server actor. This is a bit different way that you can create your actor just to provide different approach. So I create my actor, and now I run send my request, and all the requests are run asynchronously inside the body of my actor. So this is pretty cool. So this is actually a gotcha. So inside the actor, use the pipe2 to run asynchronous computation. All right, so far we talked about sending messages, receive messages. Let's talk briefly about spawning a message, an actor inside an actor. So as I mentioned in the slide, there is this relation between actor. So an actor can be parent, considered a parent, and can span child. And when you span a child, you can see in line 30, this actor really belong to the root of the nodes, which is your parents. So in this case, I spawn two actors, the spawn printer and the actor. Actually, I spawn the spawn printer actor inside the body of the actor parents in this case. And what I'm expecting here is that the actor parents really take control on the child. And this is just to introduce the next example, talking about supervision. But right now I have two actors, the child and the parents. And you can see here in line 44 that I highlight, I can reference the actor using the location transparency and the path, and I pass in the parents and the child because the child belongs to the parents, right? So now I can get a reference to the child, and I can send message to my child, or I can get a reference to my parents, and when I send the message to the parents, in this case, I write my logic that the parents also can send message to the child. So just provide to demonstrate how hierarchy can be created in Akka.NET. So important example, supervision. This is I use this code sample in the slide, but this is a very powerful concept about supervision. It's building in Akka, and really what provides is the ability in a very simple way to apply strategy to our actor, how to react if something goes wrong, right? So in this case, I create an option, and the strategy is 1-for-1, and for any kind of exception in this specific scenario, I restart the actor. But I can use more sophisticated strategy, analyze what kind of exception the actor throws, and apply different kind of strategy. So if I run this code sample in the RAPL here, I'm expecting if I pass the print message, the actor receive the print message and print in the RAPL the message I pass. If I send the boom message, my actor throw an exception. So in a classic world, this is a possibly crash down your actor and possibly all your process. But in this case, the supervisor strategy is gonna take action, and in this case, gonna restart my actor. So if I send print to my actor again, it's print hello as expected. If I send boom here, oh no, I get an exception, and the message is oops as I pass. And at this point, I know my strategy kick in and restart my actor. So if I send again to print a message to my actor, they say, well, I'm back. So this is pretty cool. More sophisticated example is using the actor supervisor, a more complex, actor supervisor. So in this case, I create two actors. One child that belongs to my supervisor actor. In this case, my child is work fun. And just receive a message and store, a state inside the body of the mailbox, which again, because if it's a mutable, is thread safe, so it's okay to use mutable type inside my actor. Then I create my system, my strategy in this case. If I run in an arithmetic exception, I'm gonna resume the actor. And the supervisor, I use the span option function, which is gonna create an action, an actor, passing also some option. In this case, I'm passing my strategy option. So let's load all this sample code in my RAPL here. So what I want to demonstrate is the difference between the resume and restart. So the resume is a very powerful. The difference is that the supervisor resume the actor keeping the same state that was inside the actor. So if the actor throw an exception, the supervisor resume the actor keeping the same state intact. Versus the restart, it creates a new actor and the original state is lost. So I pass 5, which is okay. If I pass a number is negative, I'm expecting an arithmetic exception, and my supervisor kick in and resume the actor. And because my strategy was to resume the actor, as you can see in a RAPL here, it keeps intact the state of my actor, which is pretty cool, right? If I change this with restart, well, you can imagine the behavior right now. I run again in my code, in my RAPL here. I pass a positive number, so I return 5 as expected. But if I pass a negative number, an exception is thrown, and because the strategy is different, they have to restart it, and the state is lost. So I have only a few minutes left, so I want to show two very important other projects. Well, first of all, chat system. I think probably this is mandatory. I demonstrate here how you can use your Fluent API to configure your actor system. In this case, I create an actor, a system that is listening on port 8081 in localhost. And of course, I have my chat server that receive income messages and take some action, register my client, chat client, or display some login and so on. So let's run the chat server. The chat client, as you can imagine, I start the chat client, setting my username. I set the system here to listen in localhost, and it's just a simple actor that you take the server actor right now listening using the address, and this is to demonstrate how easy to implement actor that communicate cross-boundary, cross-process. Then when I set my username, the client, it just send the connection request to the server, then make my registration. And then I loop to my client and send out my messages. So let's run 2 instances of this. Take 2 actions. So I have my server running here. I have my 2 clients. So my username here is Ricky, and the other name is Ryan. Right. So they're both connected. My server log out that Ryan and Ricky are connected. So now the 2 can send messages to each other. And Ricky receives a message, "Hi Ricky," and Ricky from Italy. So I say, "Ciao Ryan." And I receive the message from Ricky. So really simple application how you can communicate cross platform, right? I want to move something, 2 last example, very powerful. One is, I think they're going to blow your mind, is the remote in deploying. So and you can see here, I create a system using a configuration that I use a string. And this is a very powerful concept because think about, you can put this string in external file. It changes the behavior of your system, of your Akka.NET, just modify the file system without redeploying or recompile your code. So I'm going to span. No, actually, this is. I want to show this one. That's better. Yeah. So I will span a process that will run the console Akka. In this case, the console Akka, enough implemented, just run a system and listening. So there is no implementation of any actor, it's just a system running. And you can see there is no reference here in my project to any sort of other project that can create actor for me. So this is just a pure, a simple system listening. So the magic here, I have 2 helper functions just to return deploy type, which is a remote scope of the address that I'm passing. So it creates some sort of the deployment functionality. This function used in line 38 spawn E that you use in an F# API to deploy an actor, right? So I create my system, and here what the magic comes is that I can create this actor. In this case, just pass a function, and I using the code quotation, I serialize all the actors together. and send it to my local listener, to the remote listener, which received this message, deserialize the actor and run. So again, my my processor is just a system, doesn't have any logic built in. Now I create my actor. Now at this point, I send this code to the RAPL and I deploy to the actor to my console, my other processor listening. So at this point, this processor has received the actor, the serializer, and now is using it. So if I send the message, I'm expecting that my console is receive a message. And voila, receive hello. So I think it's pretty cool how you can deploy remotely an actor without, just without create any code, just sending an actor that can be deserialized remotely. I'm gonna bypass this example, but I want to run something cool. But the other example is and again, you can download this code sample and run it. But this is a more sophisticated actor, just to prove that you cannot just pass the classic example, print something. But this is a full-blown actor sent remotely with full functionality that can be sent in serialized. So far we discussed about supervision, remoting. So I want to run an example that I think is very cool. So this is the Fractal project. So there are 3 projects. One is the shared Fractal that are just some utility, right? So there are some record type that we use to pass messages between the actor in a and because F# actor API, you can send, of course, primitive of the F# languages such as record type and discriminator union and so on. So this is pretty cool. I have some utility here, and here is an actor that what I do, I receive a render tile. In this case, is this record type, which is some information, some coordinated insights, and create some images and create a byte from the Mandelbrot set, which is a copy functionality that is written in C#, probably not very high performance, but just for the sake of the presentation is enough. It's good enough. Then I have my Fractal remote, which you can see here. It's pretty cool. It just spawned a system waiting for something, right? And you can see here there are no reference to our shared Fractal to get reference for any actor. So this is going to be up and running, listening in port 1891, and all the core of the project is in our Fractal project here. So there is some WinForm to render some image here, but the interesting part is my configuration, of course, to create my system. I create my Fractal system, pass some information about my current picture box in a WinForm to render some images. Then I have I create a render tile function here that receive a record type render tile, use some functionality to convert the bytes in image and render to the WinForm. The tile, display tile, is an actor that receive the message. I use this function that I just create here to display the image to my WinForm. And interesting, line 110, I use dispatcher option, which is run in a local, in a current, sorry, no local synchronization context. So there is no problem with Marshall threads between, the WinForm. It doesn't create any thread corrupted error. I have deployment to deploy my actor remotely functionality. I create a round robin with one instance, and then I create my actor here and serialize the actor, tile render, send it to my remote system listening, which is deserialize the actor and start running. So let's run this application. I'm going to start my Fractal remote. So now the system is up and running, and again, it doesn't know anything about any actor. The Fractal here is start the WinForm application, and you're going to receive messages, and you can see the worker actor. Oops, sorry. Oh no. Oh, I lost the best part. Okay, sorry about that. So as you can see, the actor, the remote actor, it didn't know anything about any actor, but right now it printing a console some sort of information, right, that is running. So and now I'm printing, I'm rendering some image in my WinForm, right? So I think this is pretty cool how you can deploy remote an actor. The actor display render some processing and render back the result to render in WinForm an image. I think this is pretty cool. But check it out. This make one line at a time, very slow. Actor model is about building something fast. So I just changing line 124. I'm gonna create 16. I change from 1 to 16, and this in this case, my remote system, it will create 16 instances of the same actor, tile render actor, that are waiting, and the system is going to dispatch each messages in a round robin fashion. So 16 instances of my remote actor will be able to receive the message and process the message in parallel, right? So I'm expecting a little bit of boost of speed. All right, so let's go to the Fractal and run my Fractal here. Right, so let's see. Well, there is some speed improvement, right? There you go. See, it's getting faster because right now, even with my task manager, I'm expecting 100% usage of CPU. Yeah, there you go. And just with one little change, I'm able to change the behavior of my my system to run 6 instances. And you can set this round robin or any kind of setting in a config file and changing using the file system. So I think this is pretty cool. All right. So this is the code example that I have here. I'll be back to my slide here and see. Well, I think at this point I'm probably running my PowerPoint, but okay. There are, to summarize, let me see that actor modeling provides a great way to scale your application in a current request, in a current domain of today in the distributed system. Gotcha. Best practice here is that best practice here. I hope you can see this. Try to, because you can build so many actor with very low memory payload, build as much as you want to. Just keep with a with a sync responsibility principle in mind, and so you can specialize your actor. And the reason because could be a good practice is because then it's easier for you to compose different actors, and actors send messages to each other, and be easier to reason about your program. And supervisor, don't be cheap. Just create as many supervisors as you want. Each supervisor can have only one specific strategy to apply. So create as many supervisors, as many strategies you think you need in your application. The only downside that I can see about Actor in general is that when you need some sort of synchronization between components, and that can be when you run you accept some you're in a transaction situation, so you have the double phase approve between components to approve the transaction. That's the only problem that I see so far. It might be other, I don't know. So again, that's all I got. I covered as much as I could. I went 10 minutes over time, but if you have any question, I'm here. And references, this is my information, my email, and the GitHub account where you can grab the code to play with. So please download all the code, and the code sample and the slides will be there shortly as I will conclude here the presentation. So, Ryan, your turn. Yeah, I don't know if you have any question.
No, that was fantastic. I don't see any questions on either Twitter or in the Q&A section of the Hangout. So it looks like you must have answered all the questions satisfactorily. So
yeah, I mentioned this was like in the beginning over 2-hour presentation. So I really tried to narrow down the core, the more important thing, and I try, and try to slow down by my Italian accent and my, fast, talking. Hopefully, I didn't confuse somebody. But send me an email if any question, or tweet me. I'll be happy to answer anybody. But
well, that was quite good. So thank you very, very much, Riccardo, for joining us today.
All right. Thank you for having me. Yep.
And have a happy St. Patrick's Day, and look for additional Community for F# hangouts coming up soon.
Can I say something?
Certainly.
Okay. So I'm very excited. I want to promote one thing that I will start actually the next week, the 27th. I will start sort of European tour like Matthias did in the last fall. So I'll be in 10 different countries from Italy in LambdaCon talking about it will be 2 different talks. One, F# on the web that actually Ryan helped me a little bit, and Akka, Akka.net as well. And I will be in Paris, Berlin, Amsterdam. I'll be in London when this year will be the first F# exchange. So I'm very excited. If you're in the area, come check it out.
That's excellent.
Yep.
Well, thank you again, sir, and have a wonderful day.
All right, you too, Ryan. Thank you. Bye-bye.
Thank you.